Great.
Okay, let's get started. So we'll finish up what we were discussing last week, which was this Wilkinson power divider, which had most of the ideal properties we sort of wanted from this 3-4 power divider. That it should be matched, and it should be should have isolation, and also that it is lossless. And in this case, as we discussed, it's lossless in a special way, but in the most commonly used, which is basically when you're sending input from one end and you're taking equal powers out. And that's because the only loss element in this system is this resistor, which is across these two output arms. And in the ideal case, the signal on both the output arms are going to be the same, and hence the resistor never comes into play. So only when things are imbalanced, the resistor comes into play. So that happens if you're sending signals from the output, so using it in reverse, or if you're only sending signals on only one of them, or if you leave ports unterminated so that you have reflected waves coming in. Okay. So we had started using this even odd mode analysis last time. I'll quickly go over the initial part so that we are all on the same page. And the idea here is that it uses this symmetry which you have along, this line through the middle here, horizontal line, and then you separate your primary excitation, where you're basically using this 3-port model, and you're exciting one of the ports with some voltage on the output side, and the other port is 0 volts. But we change that into an equivalent even and odd mode excitation. So here, even and odd basically means that whether both the ports have the same voltage, the same sign, or they have the same voltage and opposite sign. Right? So that's what's there in these boxes here. And again, to reiterate that even though the normal mode of operation of this device, which is the splitter, you put the input on the left side and take the output on the right side, we are actually doing the calculation the other way because it's easier to analyze the system. And because it's symmetric, you expect this network to be symmetric. You can essentially, if you calculate S12, you can know that S21 is the same as S12. So the analytical calculation will allow us to derive these ideal S matrix elements. That's exactly what we are trying to do. So we started by looking at the even mode, where the two voltages here, VG2 and VG3, are equal and of value 2 V0. And in this case, the center point here can be considered to be an open circuit, right? So we looked at these equivalent circuits here, where we said that for the even mode, we're going to consider these points as open circuits. And for the odd mode, we're going to consider these points as short circuits. So short circuit, so again, I keep saying short circuit, but shorter to ground. What we are really saying is that that point is at zero potential. And that's because the points on either side of that point are always going to have equal and opposite voltage. So that ensures that this is always going to be at zero. So we then arrive at these two simpler circuits, which we use to compute the S parameters. And the even odd method basically says that you compute the response for the even, you compute the response for the odd. And then when you add those responses up, you get the response of the system you are actually looking at, which is basically with excitation in one of them. And remember, all of this works because this is a linear system. You can just superpose these results on top of each other. So, yes, so we were at this point here. Yeah, I should. Yeah. So let's go through this again. We have the source, effective source voltage as being 2 V0 for 1/2 of this even mode circuit. No current flows through R/2, so this is written as open. So basically, you can forget this resistor because it's sort of just dangling there. And then we first compute the impedance looking into port 2. Okay, that is basically here. And they call that as Z in, sorry, wait a second now, which is port 2. Yeah. Yeah, that's right. So Z in even mode into port 2, what you have is, so that's basically looking in this direction. You have a 2 ohm resistor. And again, if you forget from last time, we had normalized these resistors. So 50 ohm becomes 1. This is a 100 ohm resistor because we had separated the circuit into 2 halves. And we put 50 ohm, 200 ohms in parallel, which gives you 50 ohms, right? So that's how this became 2 here. So what we are looking at is a 2 ohm resistor being transformed by a λ/4 section with characteristic impedance Z. So the central section, which is a λ/4 section, has been just given this Z. And this again is with reference to 50 ohms. So if Z was 1, then the actual value would be 50 ohms. So we just keep it because we want to find out what value of Z should we be using. So then from the impedance transformer, we know that the transformer impedance is equal to the square root of the Z1 and Z2, one is matching, which means right. So here we are trying to find the transformed impedance, which is basically going to be the transformer impedance squared divided by one of the other. So it's Z square over 2. So that gives you the impedance at this particular point here. Okay. Is that clear? That would be, so it's basically 2 ohms and lambda by 4 of characteristic impedance Z. This is Z in is equal to Z square over 2. So once you have that, if you now use a value of Z equal to root 2, then this impedance would look like 1. Right? So Z square over 2 will be 1 if Z is root 2. Why do we want 1? Because this is 1. So we are trying to derive now the matching condition for this port because everything else is matched. So we want this port to be matched. And remember, right now we are only talking about this port being matched for the even mode excitation. So we will have to ensure this for the odd mode excitation as well. Only then it will be matched in both in the most general case. Okay. So just to summarize here, impedance true transformed by Z becomes Z square over 2, and we would like Z square over 2 to be equal to 1 so that it's matched. So that gives you Z equal to root 2. So that's why we first get that this section in the middle needs to have a characteristic impedance of 50 into root 2. So the next step is to find these voltages at either point. Now, because the input voltage here is 2 V0, and we now have a matched circuit. So we have assumed Z equal to root 2 now. We now have a matched circuit here, which gives you effective impedance 1. Then that at this point, port 2, which is written as V2E here in this little thing over there, that voltage is going to be just half of the voltage because it's 2 1 ohm resistors in series. It's a simple voltage divider. So this V2E is basically going to be just V0. Okay, that's the voltage at this point. So that's what's written here since C is 1. R by 2 is anyway not considered. Then we want to use the transmission line equations to compute V1E. What is V1E? V1E is the voltage on this side. Because once we do that, we know what's the voltage on one port and we know what's the voltage on the other port. We can basically calculate the S matrix from that. So this is slightly more involved. So they have defined the point port 1 as x equal to 0 and port 2 as x equal to minus lambda by 4. Because that's the length of the transmission line. We are going from one side of the transmission line to another side. And then you have your transmission line equation, which says that, okay, you have an incident wave, and then the total voltage at any point is going to be the sum of the incident and the reflected wave. And the reflected wave is just given here as whatever is incident multiplied by a factor gamma, which is the reflection coefficient at that particular port. Right? So we have just taken out an overall coefficient here because there's only one incident wave we are talking about right now. So from here, V2, which is x equal to minus lambda by 4, is given by this expression, which is basically by plugging in x equal to minus lambda by 4 here and beta. And that has to be equal to V0 because we have already established this, right? So this gives us one relationship between V0, gamma, and V plus. And then V1E, which is the voltage here, is V of 0 because that's what we define x of 0 here. And that's V plus 1 plus gamma. And then you substitute from the previous equation. You get that V1E is J V0 gamma plus 1 over gamma minus 1. So now you have both V2 and V1. The only thing we don't know yet is what gamma is. Okay. Now gamma is the reflection coefficient seen at port 1 looking towards the resistor of normalized value 2. What does that mean? Port 1 is here. It's the reflection coefficient measured at this junction in this way. So you have a wave propagating on a transmission line of characteristic impedance Z, which is root 2. And it's being terminated with a resistor of resistance 2. Okay. So Z naught is root 2 and Z load is 2. So that's where you get the expression for gamma here. So Z naught, Z over, Z load over Z naught over Z load plus Z naught. Okay, so this part is clear. This is basically the reflection coefficient at this point, as shown by this arrow here. So now you have your value of gamma. You plug that back into expression for V1E and you get this. The V1E is J V0 over root 2. And remember, V0 was related to the original voltage you had set up. And you also have the value for V2, which is nothing. V2E is also this V0. So we now know V2E and V1E. And basically, effectively, both are in terms of V0. So we know the ratio. So this is essentially related to the S matrix of those two ports. So the same thing is now repeated for the odd mode because we have to make them self-consistent for impedances. And you have to make sure that the total voltage we are getting at any ports is going to be the sum of these two effects. So for odd mode, we already know this, Vg2 is minus Vg3 equals to V0. So V2 0 is going to be always minus V3. So there's a voltage null. This is what we have said, middle of the circuit. We bisect it and we basically get this effective circuit now. Right? The lower one. Okay. So here we cannot remove this resistor R by 2, unlike the case of the odd mode, the even mode, because the R by 2 was there was no current passing through it. Now there is a current through the resistor R by 2 into ground. In fact, it's the odd mode calculation which is going to allow us to set a value of R, this small r, because we still don't know that. So now we say looking into port 2, we see an impedance of R by 2 since the parallel connector transmission line is lambda by 4 long and shorted at port 1. Maybe here should redraw that figure. So let's draw this here. So this is 2. And it's actually shorted to ground. There is lambda by 4 section. Characteristic impedance Z, which is equal to root 2. Then there is a resistor R by 2. Right, to ground. You have V0. So what he's saying is that since this point is a short and a lambda by 4 also, it's called the impedance inverter, right? So a short will become an open at this point. This point onwards to the left, the rest of the circuit just looks like an open circuit. So then you forget about that because an open circuit is basically infinite impedance. What you have left is this 1 ohm resistor via R by 2 to ground. Okay, so this is what it's saying here. Looks like an open circuit port. Thus, port 2 will be matched for odd mode excitation if we select R equal to 2. Why? Because this is 1 ohm. So then this has to be also 1 ohm in order for it to be matched. So
this will go only for a certain frequencies, maximum some range, it being an open circuit.
That's right. But we are only talking about the frequencies of the ideal operation. right? So last time also we said that the entire analysis assumes we are operating at that special frequency. That's where the S matrix we are deriving is actually going to work. Okay, so a little bit later we will actually draw the circuit in microwave office and see. And just like all such microwave circuits which use impedance transformers or any other transformers, there will be a frequency dependent. Things will not work, and many things will not work, right? So there are so many things which could go wrong. Matching could go wrong, isolation could go wrong, the division ratio could go wrong, the division phase shift could go wrong, and all of these will go wrong in different extents. So you again will define some reasonable range of operation which is acceptable for your application. But right now we are assuming everything is ideal. Otherwise, this calculation, you cannot do any such this kind of calculation using the most general case. So from the matching condition for the odd mode excitation, we have been able to set now the value of R. Okay, so R needs to be 2 ohms in this unit. So then if you do that, then V2 odd is V0 and V1 odd is 0, because what is V2 odd and V1 odd? They are these 2 points here. So let me. So this is V2 odd, and this is V. Sorry, right. V2 odd, and this here is V1 odd. It says port at voltage at port 2 for odd mode excitation, and voltage at port 1. V1 odd is of course 0 because it's shorted to ground at this point, and V2 odd is because of its matching is equal to 1. Sorry, equal to 2 V0 divided by 2, which is V0. Okay, so that's why we have this here. So what they're also saying is that for this mode of excitation, all the power is delivered to the R/2 resistors, right? Nothing is actually propagating beyond this point itself because of this open circuit you are seeing from the λ/4 transmission line. So nothing actually gets here for the odd mode excitation. Everything is dissipating in this R/2. So this, if we go back, when we were first looking at in the demo class for this dividers, and I was saying that there is this special case if you send inputs exactly in the even mode, then nothing gets dissipated in the resistor, and in the odd mode, everything gets dissipated in the resistor. So in the most general case, something in between will happen. So which means that for odd mode, there is no transfer of power from one port to the other. Everything is dissipated inside. So then finally, we must find the input impedance of port 1, which is basically this port, when port 2 and port 3 are terminated in matched loads. Because we have to now ensure that port 1 is also matched, right? What we have been able to do so far, that the first step we did was we tried to derive the matching condition at port 2 for the even mode excitation and for the odd mode excitation. Both gave us some conditions on the value of the characteristic impedance of the transmission line, the λ/4 transformer, and the R/2 resistor. And remember, because it's symmetric, it happens, the same thing happens on the other side also, so we don't have to independently look at that. Okay, so we now have to look at the matching of port 1. So that brings us to this equivalent circuit now. So here the values have all been put. So remember that now the input is not split into 2. We are now looking at just the regular port 1. So it has a normalized impedance of 1, which is basically 50 ohms. Then you have two λ/4 transformers of characteristic impedance √2 going like this. The R/2 was 1 ohms, so R is 2 ohms, so that's what gives you this. And then you have terminated port 2 and port 3 with matched loads 1 and 1. So we need to make sure that in this configuration, actually there's nothing left to calculate. All the numbers in this circuit have already been designed. So we just have to verify that under this condition, when we look at the input impedance as shown here, this should look like 1 ohm, right? So here we again do a simplification that because of the symmetry, the voltages at port 2 and port 3 are always going to be the same. We basically get rid of that resistor, this 2 ohm resistor. That's what's happened here in the next diagram below. So now it simplifies. So now it's very easy because you have two parallel paths of 1 ohm with an impedance transformer of lambda by 4 transformer of characteristic impedance √2. So what's going to be the input impedance here for one of the paths? It's going to be √2 square. Keep forgetting this. Z transformer square is Z1, Z2. Yes, so yeah, √2 square over 1. And this one is also going to be √2 square over 1. So this is basically 2. And that's also 2. And they are in parallel. So you get the total as 1. So that's what's calculated here. Zn is this one. So, yeah.
You want a recording audio?
Oh, I am. Oh, it's on a different laptop. That laptop is recording. Yeah. Yeah, the screen is from that one. This is basically brilliance of TIFR bureaucracy in play, and the fact that I don't have a PC Windows. Auditorium staff will not give me the correct adapter which will work on my Mac. I have one of my own that doesn't work with this projector. Right. So now summarizing all of this in terms of S parameters, we have established that all 3 ports are matched when the other 2 ports are also terminated with matched load, so which we verified. Then, with the help of these 2 equations, where we derived this one, V1E equals to JV V0 into √2, and the fact that in the odd mode, V1 was 0. V1 odd. So see, in even mode V2 was V0. Odd mode V2 was also V0. Okay, so let me write down here. V2E was V0. V2O was also V0. V1E was minus J V0 2 over not over into √2. And V1 odd is 0. And remember that here, because of everything is being matched, there are no incident reflected waves. There's only waves going in one direction. So the S parameter is just the ratio of those voltages at that particular point. So what have they written here? That S12, which is into 1 from 2, right? So the target is 1. So which is why the numerator has V1E plus V1O, because you have to add the even and odd mode excitations, and you divide by V2E plus V2O, which gives you basically 1 over √2 in voltage, which is 1 over 2 in power. The same calculation works for 1, 3 because 2 and 3 are basically the same, depending on it's above the plane of bisection or not. And this part here is basically where we are using the symmetry, that is a linear circuit. So these S matrices must be symmetric. And the last part is related to the isolation part. Okay. That S23 and S32 are 0. Why is that? Because in the case of even mode excitation, this middle point here is open. So the other circuit is sort of disconnected, the lower half. And the lower half contains what? It contains port 3. So there is no power flow going across from one to the other. And for the odd mode also, it's not going because there is a connection to ground. So both the fact that you can either have an open circuit or short to ground isolates these two circuits completely. So nothing you send on port 2 will arrive at port 1 and vice versa because of symmetry. So this basically completes your all your S matrix elements, right? So it's a 3 by 3 matrix. It should be 9 elements. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So by using this even odd mode analysis method, you have been able to derive this thing. But again, this is a good thing to know and understand, and I would suggest that you go through this calculation yourself. There are several more examples in this chapter where they apply the same method, and you can go through that, but we will not go through in detail the step-by-step of how this is done. So hopefully this gives you the flavor of what you need to do when you separate it into an even odd. This cannot work every time. That circuit has to have some special symmetry, or you have to identify that line of symmetry where you can apply this. And then that simplifies the circuit and you can go ahead and do the calculation. But if you have access to a software like Microwave Office, you can just draw it and you can get the answers. But this kind of analysis also gives you an intuition about what's actually going on in the device. So it'll help you to construct your own circuits in the future if you do it. So, I mean, just to give an example, in one of my students who graduated recently, Sumeru, he applied this even mode analysis to this circuit, which we call the ring coupler. It's a circular thing with 2 ports, and so it has again an axis of symmetry. So using that, he was able to analytically work out some formulas, which again gave us intuition of why this circuit works. We knew already from Microwave Office simulations that the circuit was doing something very interesting. Just to have a more deeper understanding that why it is doing what it's doing came from doing the analytics. Okay, so wait, did you the Microwave Office is set up on? Okay, let's try that.
Even odd mode and it's symmetry for both symmetry.
This will not work. Yeah, you will have to find something different to do. But most circuits will have some axis of symmetry where you can do this. We will take a quick look at some of those. Let me. So we'll now make this circuit here and also try to see some of the assumptions or things we obtained from the even odd mode analysis, right? So we can see that it actually indeed works the way we have calculated here. to 6 gigahertz as the operating frequency, and it's 90 degrees. We have port 1. So we have the 2 lambda by 4s at 6 gigahertz. Port 2. Sorry. Oh, what happened? Okay. And then the last thing left is a resistor. What's the value of this guy?
Mhm.
Which means
Why do for this?
it's 100 ohms. Right? It's 2 means 2 into 50. Okay. Define a graph. Add measurement. Schematic 1. Magnitude dB. S11. S22. S33. S12. S13. And S23. Right? It's the isolation. I could put S21 and S31 for symmetry. What did I miss? Oh, I missed S32, I guess. Okay. Since we know the operating frequency is 6, I'm going to go from like 5 to 7 to start with. Okay. Right. Let's stare at this guy. So S11 is blue colored triangle. So that's this one here. S22 and S33 are pink squares and brown diamonds. So those are these two curves here. So already you see there's something interesting. They're not the same, right? But they are the same at this point. At 6 gigahertz. I mean, this, of course, again, saying them same is a little strange because here it should have been minus infinity. Maybe it's better to look at it in linear magnitude. Let's quickly change that. So again, pink, brown, and blue. Those are these three things at the bottom. At exactly 6 gigahertz, it's 0. So that's the matching condition. And you see that the matching condition gets worse as you go away from it, but differently for port 1 and port 2 and 3. Now, port 2 and 3 are really truly symmetric, so they will have to look exactly identical, which is what you're seeing here. So it's like the port 2 and port 3 match is better, even though you go away from the frequency. Any intuition on why that's the case?
There's dissipation, so the transmission that is almost the same. So the dissipation has to come from the less.
The what is?
So there's you want to add the loss plus reflection plus transmission to 1. So there is loss there and there is no loss in post.
Can you explain in terms of what you see here? I mean, you're saying this and that, so I don't know what you're referring to.
I'm saying that port 2 and port 3 also have this dissipation.
Yes. Yes.
So if you still have to add the transmission, reflection, and loss to 1 at these 2 ports,
Yeah.
the reflection has to be less for the same transmission. And if the port 1 also has the same transmission, they can't be all the same. That's what I'm trying to say.
No, we're not talking about transmission now. We're talking about reflection. I mean, in some sense, this question really has no meaning because they are different ports. But from what you just went through in the calculation, what I'm asking is, why is port 1's matching from 50 ohms getting worse faster with frequency as opposed to that of port 2 and port 3? Port 2 and port 3 are basically the same. It's close to something Panya is saying, but she's not hitting the nail on the head.
Maybe it's just that there is a resistance and there are transmission lines. Transmission line, the thing varies faster than the resistance.
Yes, almost there. The matching condition relies a lot more heavily on the R being 100 ohms for port 2 and port 3. Whereas for port 1, it relied on the transformed impedance of the 50 ohms via the lambda by 4 transformer. Because remember that in the even and odd mode case for the matching condition, in one case, the your transmission line was involved because it appeared as an open. And in the other case, it was not even involved. So the frequency dependent component, the only frequency dependent component here is the transmission line. And it's playing a bigger role for port 1's matching condition as opposed to the port 2 and 3 because of the resistor being right at the mark. So that's basically sort of the complete picture here. Okay. But yes, what you said, Panya, is mostly correct. Then you have S21 and S12, which is the same here, and the same as S31 and S13. They're all lying on top of each other out here, and its value is 0.7, which is basically 1 over root 2, right? What we had seen before. And there is S23, which I can't seem to find. Let me. Yeah. So S23 here is again 0 at the operating frequency of the transformer, and it's non-zero at other places. So I think it seems to line up with one of these blue curves, I guess. Okay, so now we can define some tolerance range, but what you also see is that the splitting, this is 0.7042, right at 6 is 0.707. 707 is basically 1 over root 2. And this is 0.704. So it's pretty good from the point of view of the equal split, right? Let's now expand the frequency range and go from, say, 4 to 8 gigahertz. And let's go back to the dB units. I will just leave the 3 important ones and disable everything else. So S11, S22, then S12. So let's look at S11 first from the matching point of view. So usually, if you remember, the rule of thumb I've been telling you is minus 20 dB is considered pretty good. That means less than 1% power reflected. And minus 1 dB is around here, right? So this is about 5 gigahertz, of course, symmetric. So you have about minus 20 dB here. So from 5 to 7, this is pretty well matched. And if you are more allowing a little bit more, so if you go all the way here, this is still minus 15 dB. This is still most of the power is getting transmitted. The S22 is always better than that. In fact, here it's still minus 30. So S22 is almost irrelevant to worry about. So even a simple one-stage lambda by 4 transformer Wilkinson divider has what we typically call an octave band. Octave band here means a factor of 2. So 4 into 2, 8. And if you look at the splitting, so it's minus 3 dB here exactly. And it's like minus 3.1 out here. Now, this, of course, is still very ideal because the transmission lines and everything has no loss. When you make something in a circuit board, that will have some insertion loss. So that will add to the overall transmission losses. You won't get exactly this. But that's why this circuit is actually very, very popular. It works quite well for a reasonable range of frequencies, right? We can even go further out and see when does it really start getting. So from the point of view of splitting, I mean, it's pretty good even at 1 gigahertz, right? Minus 3.4 and minus 3.4. It's starting to now not look exactly symmetric on either side, but it's pretty good. And the reflection here is now, okay, now it's about, you're losing about 10% of power in reflection. So this works quite well. And again, there are simple changes you could do. You could change this transformer into a multi-section transformer because that's the only role it's playing, right? Its entire purpose is to give you this, the transformation you get from a lambda by 4 section. So if you do it in multiple steps, it should also work, provided you keep all the phases in match. So that will allow you to push the bandwidth more. So in a practical or a commercial device which uses Wilkinson techniques, you might have multiple sections of these things to give you a very broadband kind of performance. But I think the ones I showed you, which are from this company called Mini Circuits, is probably doesn't have too many sections over there. Okay, so now let's see how to check the some of the assumptions we made. I really do that. me try something. I'm going to make a new graph. Show you a new type of measurement. Let's see if it is there. Okay. So under linear, there's something called G even, okay, whose description says even mode gamma. So this by definition takes two ports as input and calculates what would be the reflection coefficient for an even or an odd mode excitation. Okay. So when I say now first port, second port, 1 and 2, it will take port 1 and 2, give it an excitation like this and compute the reflection coefficient. So let's look at MWE. We reduce the frequency back to 4 to 8. Okay. Oh, sorry, not 1 and 3. Sorry. Output ports are port 2 and port 3, right? Okay. So even mode gamma is also 0, right? This is what we had first calculated, which is same as saying it's a matching condition. The input impedance looks like 50 ohms. Let's add odd mode gamma. And even that is 0, which is what we expect for this case. So we have just now independently verified for the individual ports, but also for even an odd mode excitation, which anyway had to be the same. I was actually had a thought of making this circuit into the two parts. Will that work here? G, yeah, G even. And it comes under linear. Okay. Whereas the standard port parameters are inside linear, there is port parameters, and then you choose S. Okay. So okay, maybe I will give. I thought I'd figured it out, but now suddenly I'm not sure. Maybe once I figure it out, I'll give it as in the assignment. So let's now move on to some more of these devices.